All right, we've seen now how a basis can be used to express any vector as a column vector. Remember what this means up here. If I have a vector v in a vector space, which is expressed as a linear combination of a basis, that's what this on the right-hand side is talking about. This right-hand side means that the vector v is alpha 1 b1 plus alpha 2 b2, etc. And these b's here are vectors. They could be matrices, they could be polynomials, they could be any kind of vector. So any vector that's a linear combination expressed in terms of a basis, we can write as a column vector where the components of the column vector are the coefficients in this basis expression. So when we express the column vector, remember we have to make sure to tell what basis we're talking about. All right, so that is kind of this notation. Let's see how this representation applies to linear operators, linear maps. Now, a linear map or operator goes from one vector space to another, and these two vector spaces can both have their own bases. They don't have to have the same basis because they could be different bases. They could be different vector spaces. For instance, V could be a vector space of polynomials, and W could be a vector space of functions. So these different vector spaces will each have their own basis. And this linear operator will take vectors in here to vectors in here. So in other words, it will take linear combinations of basis vectors here to linear combinations of basis vectors here. All right, now we can associate with this linear operator L a matrix. And the entries of the matrix are specified as follows. Take each individual basis element in the basis of V, find out where it goes to in W, and then take the basis representation of that image vector in W. We can express this equation pictorially this way. All right, here's our domain V, here's our codomain W. And here I have two different basis vectors, B1 and Bj. B1 goes over here in W according to the linear transformation L. Right? L is represented by these arrows. L of B1 is this linear combination. L of Bj is this linear combination. Notice that the subscript, which is the column index, represents the image of, it corresponds to the index of the basis vector in V, and the row index corresponds to the basis vector in W. That's in the linear combination for each basis vector of V. All right, so let's go back. So calculating this matrix, all we have to do is take the basis vectors in V one by one, compute their linear transform, and then express that linear transformation of B1 in terms of the basis entries of W, find the basis representation of LB2 in terms of the basis vectors in W, and so on. So it might be a lot of computation, but the procedure is very step by step. So again, this here is the linear combination of the basis vectors in W. This first vector here represents LB1. This second vector here represents LB2, and so on. And then we arrange all of these, since all of them have B1, B2, dot, 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 up to Bn, as the row vector multiplying, we take that out once and write the other columns next to each other to give us a matrix that corresponds to the linear transformation. All right, this all seems very abstract. Let's look at a particular example. All right, so we have from L, V goes to R3, and V is a hyperplane spanned by the two basis vectors 1, 1, 0 and 0, 1, 1. So to express the linear transformation L, it's enough to express L on those two basis vectors. And suppose in this case, the linear transformation of 1, 1, 0 is 0, 1, 0. The linear transformation of 0, 1, 1 is also 0, 1, 0. All right? So we have our linear transformation specified on our two basis vectors. Now, according to linearity, we can write the linear transformation on a linear combination is equal to the linear combination of the linear transformations. So now let's see how we express this as a matrix using the bases that we have available to us. All right, so we know that 1, 1, 0 and 0, 1, 1 are the two basis vectors. We'll use as the output basis our standard basis. Now LB1 is just 0E1 plus 1E2 plus 0E3. That expresses that the transform of B1 is the column vector 0, 1, 0. And similarly for LB2. All right, so if we write LB1 next to LB2, we get these two vectors here. And we group the two row vectors together, and we write the column vectors next to each other, so we get this matrix here. So this matrix corresponds to that linear transformation relative to the two bases, to the basis B in the domain and the basis E in the codomain. All right, so we can write that this way. L operating on any vector xy expressed in basis B can be expressed in basis E as this matrix times xy. All right, so that shows how the matrix can be used to find the linear transformation relative to input and output bases. All right, so summarize the point. Linear operators become matrices when given ordered input and output bases. The order in which you specify the basis does matter. Let's look at another example. Here our vector space V in the domain is a vector space of polynomials. And we've seen that this vector space of polynomials has a basis 1xx squared. So the coefficients a, b, c correspond to a times 1 plus b times x plus c times x squared. Now if we take the derivative of a plus bx plus cx squared, we get this polynomial b plus 2cx, which in the same basis is expressed as b 2c 0, right? b comes from b times 1, 2c comes from 2cx. All right, so we're using the same basis for the domain and for the range. Now, since the linear transformation of the basis 1, 0, 0, well, what does 1, 0, 0 go to? Well, notice that there's no a here at all. And so if I have 1, 0, 0, then b is 0, c is 0, the output is 0. So if I input 1, 0, 0, the output is 0, 0, 0 relative to the same basis. That's why this first column is 0, 0, 0. Now suppose I input instead 0, 1, 0. What's the output? Well, if I input 0, 1, 0, I'm going to get 1, 0, 0. That's this second column here. Finally, if my input is 0, 0, 1, then the output is going to be 0, 2, c 0. That's this third column here. Okay, so we see how the matrix corresponds to this linear transformation with the caveat that we have to specify the basis, and the basis for the domain and for the range was 1x x squared. Okay, that's it.